playing.
If I see one.
This episode of Physics Honors brought to you by Coca-Cola.
You just kind of plan to match today?
Yeah.
We all just eggs for
every
Bruce.
day.
Matt, shut your mouth.
What you mean, bro?
I almost wore.
Stop
you told me
talking
one of my
to the
bands.
camera.
I wanted to wear. I didn't want to
We
wear.
all
like
just
one,
eggs
so
for
I
Bruce.
had to go up kind of, and my band would rub me right here and it hurts. So I
Okay.
decided not to.
Okay.
Going to the game?
Eggs for real.
I don't know. I'll see how my back.
Depends how his back's feeling. Yeah, the doctor.
Do you have one of those?
Just
like,
get it
portable
amputated.
things?
I'll let you play on the drum line.
Oh, okay.
I'll let you play. You can carry a bass drum. That will really help.
Oh, his back will feel real nice.
Yes.
You just sit really close, you can sit against the defense or the.
How about
Oh,
you step on my back?
Max, dude,
And next year they'll have seats in there.
Roll it out.
Okay. All right, so let's chit chat about the next big thing, which is going to be momentum. So if you look at what we have left, as Olivia pointed out, we've got like what, 2 weeks and then Thanksgiving, and after that we've got like 3 weeks. So basically, here's what we got to get through. We got a big test over momentum. Momentum takes about 8 days to get through because you've got to do linear and angular momentum. And then we've got a big unit on energy, and then we've got to finish up with like some gas laws and thermodynamic stuff. So in terms of like really big tests, we only have one kind of really big test on momentum. Tests on energy and stuff tend to be a little bit smaller. And then at the end of the term, you're going to have a lab final that's 10% of your grade, and a written final that is comprehensive and that's going to cover 15% of your grade. So there's all of that.
Are they in class?
Yeah, yeah, it's all done.
Take home last.
Yeah, no, I'm going to give you your take-home final. It's a
Yeah,
take-home final.
That'll be great.
No.
Epic.
Okay. So let's talk about momentum. So momentum is one of those terms that like sportscasters tend to use as a go, and you can feel it if you've watched sporting events. You can feel like literally when a team has momentum. Okay, you can sense that, or when they've lost momentum. Okay, so all the physicists in the world go, you really can't quantify it that way. So from a physics perspective, momentum is as simple as it can possibly get. It's just mass times velocity. Okay, that's it. That's all momentum. There's not one half. There's nothing. Okay, you don't have to worry about acceleration. It's just mass times velocity. It is literally as simple as it can get. Now the question is, everybody asks, look, why do we use M for momentum? Well, the reason being is then it gets confusing, and then you have M equals mv, and you don't know what's what. And so they used the P because it came from the old concept of momentum, which was known as impetus. Okay, so impetus was this idea where when you threw something, you gave it a certain amount of impetus, and when that impetus ran out, it stopped. So if I take this golf ball and I roll it, I give it a certain amount of impetus, and as soon as that impetus runs out, the bowling ball is going to stop. Okay, or the golf ball is going to stop, whatever it is. So you can think of like impetus as being like a tank. Okay, it's like how much fuel is in the tank. Well, it's how much impetus is in the impetus tank. So if I throw it really, really hard, I've given it a lot of impetus, and it's going to go a long way before it runs out. Okay, and you can think of it in terms of like kicking a football, a volleyball, whatever it is. Okay, your car. You fill up your car with impetus. How far can your car go on a tank? So that's where that P comes from. Now, in terms of calculations, it's as simple as it can possibly get. So let's say that I have a 1 kilogram mass, and I'm going to make it move at 5 meters per second. Okay, how simple was that? So I got a 1 kilogram mass moving at 5 meters per second. Oddly enough, I get 5. But now, what units do I get?
Newton seconds.
Well, the simplest one is I get kilogram meters per second. Okay? Literally, that is as simple as it can possibly get. Now, is this the same as force.
No.
No.
Because force is kilograms meters per
Second
Second
squared.
squared. Okay? So this is one option for momentum. Kilogram meter seconds, it's simple because it's mass times velocity. Home run. Now, the other thing that you can do, and later on you'll see why this works as well, and how we get to units. But you can also write it as Newton seconds, and here's why this works. Because newtons are kilograms meters per second squared, and if you multiply that by seconds, one of those cancels out, and you get kilogram meters per second, which is the same thing as this, okay? So it's a personal preference thing. I don't care if you use Newton seconds, I don't care if you use kilogram meters per second. Make a decision. I don't care, okay? Just pick one. Personally, I prefer Newton seconds, but that's just me. Okay. So, can momentum ever be negative?
Yes,
Yeah.
because velocity can be negative.
Yeah. So if I define this direction as being positive, right? Okay. Then if I change the direction and make it go back this way at negative 5 meters per second, oh, okay, right. Then the only thing that would change is I would have 1 kilogram times a negative 5 meters per second, and oddly enough, I would get negative 5 Newton seconds. So, because momentum can be positive or negative, do you think momentum is a vector quantity or a scalar quantity?
Vector.
Yeah. So, if I've got a certain momentum going this way, it's going like this. If I've got a momentum vector going that way, it's going in that direction. Okay, pretty simple. So, is it possible for two objects of unequal mass, let's say for example the golf ball, and 1 kilogram mass, is it possible for these two objects to have the same momentum?
Yes.
Great.
Yeah.
How?
That's like the speed. Like I know. Okay. I have to figure out how to word this.
Okay. I got nothing but time.
Just sit here the whole day.
Not the whole day, but can I give you a hint?
Yeah.
What are the two things that determine momentum?
Mass and velocity.
So this has a small mass.
It does have high velocity.
Ah!
That's what I was just meaning.
I know.
don't know how to say it.
I know, that's why I make the big money. Okay, so, yeah. Okay, so, since momentum is the product of two things, I can have a small object moving really fast, or I can have a large object moving really slow. Okay? There you go. Now, what if both objects, mass, the large mass and the small mass, are moving with the same velocity? Which one would have the greater momentum?
Bigger mass.
Bigger mass, okay? Okay, kind of cool. Now, is it possible for the golf ball and the 1 kilogram mass to ever have the same inertia?
No.
No.
Because that's a factor of mass.
Yes, because that's the only thing that determines inertia.
Mass.
Mass. So no matter how much I make it speed up, slow down, whatever, the 1 kilogram mass is never going to have the same inertia as the golf ball does. Okay? Cool with that? Okay. Now, obviously we are not going to spend 6 days learning how to multiply a mass times a velocity. Okay? I know, it'd be really easy. Here, yeah, all multiple choice questions. 5 kilogram mass is moving at 20 meters per second. What's its momentum? Okay.
I'd probably do.
Y'all can multiply two numbers together, I'm sure. Now, here's the question. Is it possible, Tori, to change the momentum of an object?
Yeah.
By doing what?
Changing the velocity.
So what is it required to change your velocity?
Change direction.
Not necessarily.
No.
Mass remains constant.
Acceleration.
Ah! What do you have to have an acceleration? Give you a hint. It rhymes with horse.
Of course.
A force! Oh, that's kind of cool. So, if I take this ball, right, and I throw it up in the air, is the momentum changing?
Yes.
Yes. Why?
Because the acceleration due to gravity is causing it to
Okay?
slow down.
So, as this thing is in the air, don't worry about me throwing it. As this thing is in the air, is the velocity ever constant?
No.
No. So, therefore, is the momentum ever constant?
No.
No. Now, here's what you're going to see. A bunch of things that we've talked about before are going to kind of get interwoven into this momentum idea. So oddly enough, you can talk about momentum in terms of a velocity time graph. Okay? So if I take this ball and throw it up in the air, okay, what's the velocity time graph going to look like, from including me throwing it? So let's say it starts at 0. I'm going to throw it, and then I'm going to catch it. So I'm here, okay, I'm going to throw it, I'm going to catch it. So obviously, where's the graph going to start?
0.
0. So let's define up as being positive. So it's going to start at 0. What's this thing going to do?
Go up.
Going to go up. Then what? This is when. Now at this point, I'm going to let go of it. I'm going to let go of the ball at this point. What's it going to do?
Go down at a constant slope.
Like this?
Yeah.
Pretend that that's the slope. Where's the ball at this point?
Max height.
Maximum height. What's the slope of this line?
Negative 9.8.
Negative 9.8 meters per second squared. At this point, I catch it. What's it going to do?
Stop.
And go up like this. So, is the velocity ever constant?
No.
No. Velocity is always changing. First, I make it get bigger, then it gets smaller, then it gets bigger. Then I stop it, and it goes back to 0. Okay? Now, if the velocity is always changing, then what else is always changing?
Momentum.
Momentum. Oh, okay, right. So let's talk about what the momentum time graph would look like.
So just the exactly.
Would the momentum time graph mirror the velocity time graph?
The same shape, but not the same values.
Well, if mass is the same, then shouldn't it be quite similar? Because if mass itself is constant, the only thing changing is velocity, then it's just a velocity time graph.
But the units are going to be different,
Yeah.
right? But the overall shape is going to be the same, right? So it's going to start with no momentum, and then it's going to gain some momentum, and then it's going to lose momentum, then it's going to gain momentum, then it's going to lose momentum. So your momentum time graph is going to look something like this, right? Go with this. So this is increasing my momentum. This is decreasing my momentum. So what's happening from here to here?
Negative 9.8.
I'm increasing the momentum, and then I'm decreasing the momentum. Now, an interesting thing happens, though. Interesting thing happens. What's the slope of a velocity time graph give you? Acceleration, because it's delta v over time, right? Change in velocity over time. You've all been through this 1,000 times. Oh, it happened. But here's the $1 million question. What does the slope of a momentum time graph give you?
Is it 4?
Well, what's one way that you can express newtons?
Kilograms meters per second.
Well, or
Or Newton seconds.
Newton seconds, right? Okay? Newton seconds. Hold on. And then you got time here that's going to be in seconds. So if I look at change in y over change in x, oddly enough, I get units of Newton seconds divided by,
Seconds.
oh, miracle of miracles, look what happens. Force. Now, here's what you have to understand. On a momentum time graph, if the slope of a momentum time graph changes, what does that mean in terms of the force? changes. So here I've got a positive force acting upward. Here I've got a negative force because I've got a negative slope. Here, do I still have a negative force here?
Yes.
Why?
Because there's a negative slope.
Still a negative force, right? And then I've got a positive force. Now, oddly enough, that matches up with the sign of your acceleration. Over here, what was the sign of my acceleration? Positive. What was I doing? Speeding up. Then I've got negative acceleration, so I'm slowing down, but then I start to speed up, and then I start to slow down. So, because my velocity time graph is never a horizontal line, oddly enough, my momentum time graph is never going to be a horizontal line. Okay? Now, here's what you have to understand. The slope on a momentum time graph here represents force. Okay? So guess what? If I change the slope of my momentum time graph, what have I changed?
The force.
The amount of force acting on the system. Okay? Everybody cool with that? Okay. Now, let's go back to what Smith and Torrey said. If I'm going to change the momentum, I have to change the velocity, right? If I change the velocity, that requires an acceleration, and an acceleration requires a force. Okay. So, here's what's going to happen. I'm going to throw this golf ball to Shively, okay? You're going to catch it, and then just, that's all, right? Got it? Okay, so, okay, let's try it again. Okay, so I'm here, boink, he catches it. So, assuming that the velocity of the ball stays constant in between, okay? Let's just, it's going to change a little bit, but let's just pretend it's the same. So what would the momentum time graph for that situation look like? Yeah, from the but I'm going to include my throat. Okay. What? But I'm going to include my throat. So what's this is a momentum time graph, right? So what's the initial momentum of the ball going to be? Zero. Then what's it going to do?
Spike it.
So it's going to go up, right? So what's happening during that part of it? I'm throwing it, right? I'm exerting force. I'm making it speed up. At this point, it leaves my hand. So what's it going to do?
This is for the velocity X or the
It's
velocity
either going to keep going up, it's going to go horizontal.
Let's go horizontal.
Is this for the X velocity or the Y velocity?
This is just for the momentum in the horizontal
But we're
direction.
pretending that the velocity doesn't change, right?
So they'll just keep.
Yeah, I said over this short amount of time, I'm just going to assume that the velocity is going to remain constant.
Then
Horizontal
it's just going to be a
line.
horizontal line.
So yeah, it'd be like a horizontal line. So this is when it leaves my hands, right?
Yes.
Then I got a constant momentum. Then Shively's going to catch it. So then what's it going to do?
Go down.
Straight down.
To zero.
Okay, it's going to go to zero, right? Okay. So, is there going to be a change in momentum? Yeah. So here I've got a change in momentum. Do I have momentum here?
Yes.
But is it changing?
No. So there's no change.
And then here I've got a change in momentum as well. So if you go back to what happens, if you're going to get a change in momentum, what had to happen to the ball? What had to act on it?
A force.
A force, right? This goes back to Newton's first law of motion. Objects in motion remain in motion until an outside force acts upon them. You can apply that same idea to momentum. You can basically take out the word motion and you can insert the word momentum. So if an object has momentum, it wants to maintain that momentum vector. If it doesn't have momentum, guess what? It doesn't want to get a momentum vector. Now, think about your car. In terms of momentum vectors, what's the purpose of your gas pedal?
Maintain or accelerate momentum.
To make the momentum vectors
Bigger.
bigger. What's the purpose of the brake?
Make them smaller.
Make them smaller. What's the purpose of the steering wheel?
Change the direction.
To change the direction of your momentum vectors. Okay? So you can think of your car as a momentum machine. Engine and the tires make the momentum vectors bigger, brakes make them smaller, steering wheel turns the direction of the momentum vectors. Okay?
So much horsepower.
Now, so we got this going on, right? Momentum and time. Kind of cool. Now, Charlie tossed the ball back. So if he tosses it back and I don't catch it, okay? And I don't catch it. If I don't exert a force on the ball, what does the graph do?
It's horizontal.
It remains as a horizontal line. Why?
There's no force.
There's no change in velocity because there's no force, therefore there's no change in momentum. Got that idea? Okay?
It's the wall.
Until it hits the wall. Then there's another force acting on it. Okay. Sam, stop that, or Mad Max, stop that. And let's go back through. Can you see that?
I can.
Okay.
Can you see now? Oh,
Look at all. Okay, so here's what I've got. I got 10-gram mass, this tiny little cute 10-gram mass. Okay? It's cute. I'm going to hang that from the end, right? Kind of line this up. So when I let go of this thing, is the momentum going to change?
Yeah.
Yes.
Okay? So I'm going to let go. Okay? Well, that was exciting. Okay? But here's the point. Did the momentum change?
yes.
Yes.
Yes. Now, was there a constant force being exerted on the cart?
Yes.
Yeah. Yeah. Because what was creating the force?
Gravity.
Gravity acting out here. So I've got this, here's my table, right? And I've got a cute little 10-gram mass pulling big cart up here. 10 grams is how many kilograms? 1. Yeah, so 10 grams, right? Divided by 1,000, I get 0.010 kilograms. Now, if I multiply that by the acceleration due to gravity, otherwise known as 9.8 meters per second squared, I get 0.098 newtons. True? Yes. So that's the force that's acting on the system, 0.098 newtons. When I let go of it, was the force acting on that cart the same the entire time? Yeah. Gravity was the same, less fluctuated, which hopefully it doesn't, that'd be really weird. Okay? Everything's going to stay the same. So what I can do is, I can draw this as a force-time graph. And in this case, I've got 0.098 newtons. And that thing is going to be exerted for, I don't know, let's say 3 seconds. Okay? Let's make it simple. Let's make it 2 seconds. Okay? So, could I find the area underneath that graph?
Yes.
Presume so.
Do I know a height?
Yes.
Do I know a base?
Yes.
Area of rectangle is?
Base times height.
Length times width. So if I take 0.098 times 2, I get? Now, what units?
Newton seconds.
Newton seconds.
Oh, Newton seconds. Oh. Okay? Now, technically that isn't momentum. Because what was the initial momentum of the cart?
0.
So this represents not momentum, but the change in momentum. Oh, right. So look, force times time equals change in momentum. Now, because look, if I have no net force acting on the system, how much does my momentum change? It doesn't. Because right now, the 10-gram mass is pulling on it, but guess what? We're not changing the momentum. Okay? Now, what would happen if instead of letting that happen for 2 seconds, I let it act for 4 seconds?
Get a bigger change in
Oh, we're getting a bigger change in momentum. So the longer the force acts on a system, guess what?
The bigger the
The
change.
more the momentum changes. Which is, if you drive, you know that. Because if you just barely tap your brakes, right, does your momentum change much? No, but if you hold your brakes down for a long amount of time, guess what?
Head goes through the front windshield.
Okay, that's a bit extreme. But how about your momentum changes more? Let's go with that. You take it.
Less fun, but okay.
Okay, I know. Gotcha. So, on this situation, could I draw a momentum time graph?
Oh, yeah.
Yeah.
You know,
What's my initial momentum?
0.
0. Is it going to end up with some momentum?
Yeah.
Yeah.
Yeah. Now, I don't know that because I don't know how fast it's going and I don't know the mass. But I got to figure that at the end of 2 seconds, it's going to be some value, right? Okay? Now, here's the odd thing. Here's going to be some momentum. Here's my time. Could I find the slope of that line?
Yes.
Yeah.
What units would the slope be in? No.
Newton.
Being Newtons.
Because momentum is in,
Kilograms.
this is in,
Seconds.
so I got Newton seconds over seconds. Seconds cancel out, I get units of,
Newtons.
so what's which is going to represent
Force.
force. So what do you think the slope of the line is?
0.08.
0.098 newtons. Okay? Go with that. Now, we're going to change up the system. I'm still going to keep the 10 gram mass on the end. Okay? But now, I'm going to take off the 100 kilogram, or the 1 kilogram mass, and now I'm just going to let it go like this. Okay? So now what's going to happen? It's going to go faster. You even said it faster. It's going to go faster. Just for dramatic flair, right? Okay? Now when I let go of it, it even makes that sound. Meow. Okay? NASCAR. Yeah.
What does NASCAR
Now
stand for
athletic
again?
sports center in United States. Okay.
Bro, you're kind of redneck. I don't care. It's not NASCAR.
Okay. I'll admit, I do have small hints of redneck in me. Okay? Not as much as my brother. But
Fair enough.
Bubba,
Wait, so NASCAR is non.
Felix, get your head out of the shot.
non-athletic sport centered around rednecks.
You know,
Okay.
like, just taking your RV, sitting in the middle of a track, and
Yep.
sitting there for 3 hours watching a car go around and around.
Drinking Bud Light.
There is nothing better than that.
Okay.
Oh my God. This is Stanley.
Now, here's the question. Here's the question.
I didn't notice that.
Without the 1 kilogram mass, when I let go of this cart, okay, how does this graph change?
It's a
It
slope
doesn't.
line now, right? Or whatever, right?
No,
Why?
it doesn't change.
Because it accelerates, so
It
it's
does
not
accelerate.
force.
But didn't the first cart accelerate?
No.
Really? Didn't that accelerate?
Yes.
Okay. Now, are the accelerations the same, Vaughn?
No.
Yeah, this acceleration is
Bigger.
bigger. Okay? So, here's the $1,000,000 question. Madeline, what did you say was going to happen with this graph?
Stays the same.
Why?
Because the same forces are non for the same period of time.
Is it, I still have a 10 gram mass suspended from the end. And if it still pulls for 2 seconds, guess what? It's still going to end up with the exact same force acting over the exact same period of time. Okay? Now, what's going to happen in my momentum time graph? Why? Same force over the same period of time. Okay? But, which cart is going to end up going faster?
That one.
The one with the 1 kilogram mass on it, or the one without the 1 kilogram mass?
Without.
Without,
Why?
because it has a small.
Divided by a smaller mass, so acceleration.
So here's the deal. Do they both end up, this is what's going to be important, do they both end up with the same momentum?
Yes.
Yes.
Yes, they both end up with the same momentum. This one has a much bigger mass, so it's going to end up with a
Lower velocity.
smaller velocity. So if the momentums are the same, this has a larger value for mass, so it's going to have a smaller velocity. This one is going to have a smaller mass, so it's going to end up with a
Larger velocity.
bigger velocity. Now, let's go with what Vonda said though. The forces acting on them are the same, true? Which one's going to accelerate faster? The second one. So now if you go old school and you go F equals ma, right? Same force, right? Acting on both. So you can go old school on this if you want to. Same force, smaller mass gets a
Bigger
Bigger
acceleration.
bigger acceleration. Okay? And as long as the time is the same, the one with the bigger acceleration over the same time is going to end up going faster. Okay? Cool with that?
Yeah.
Now, let's change it up. So, we'll put the 1 kilogram back up here, and we'll take off the cute little 10 gram, which is cute, but really doesn't do much for me. And let's put a 200 gram mass on the end.
Yeah.
Okay?
Yay.
If you
There
get some depth
There we go.
perception there.
Here we go. Okay, now,
You didn't touch it.
You didn't sniff the marker.
okay, just say no. Just say no.
Am I the only one or is it ring spinning?
If you have to ask, it's probably you.
That's like good life advice. If you have to ask, it's probably just you.
Yeah. Like, am I the only one here who doesn't understand?
Yeah.
Okay. All right. Not necessarily though true. Okay. Because a lot of times you're not the only one, but you're the only one that'll ask, and everybody else goes, "Oh, thank God you asked," because I don't understand either. Okay.
Love when that happens.
Yes. Because everybody's going, "Oh, thank God somebody else asked." All right.
I'm not actually a hater.
So-
I'm very glad that you want to
But
learn.
it could be, yeah. All right. So let's say I've got the 200 gram mass on the end, and now I'm going to let go of it.
Here we go.
Woo!
Here we go.
Whoa! Now,
Where was that depth
Accelerated.
perception
What's
when
gonna
you tried to
happen-
Put the weight on.
That's a
You
neat clip.
can't overcome the 200.
I think I did. Okay. So when I go with the 200,
I can't be losing.
what's going to happen to my force time graph?
The force gets bigger. So we're gonna have.
Oh! So with a 200 gram mass, what's the weight of a 200 gram mass? 0.2 times 9.8 gets me.
1.96.
Okay, look. What if it was 0.2 times 10?
I don't know what I'm saying.
2.
So it's 1.9.
Yeah, so it's 1.96, right? So that'd be 1.96. So what's going to happen to this area? It's going to go up, right? It's going to go up because now I've got 1.96 newtons. True? So what's going to happen to my momentum time graph?
The slope is gonna be steeper
Why?
because the force is bigger.
And I've got a bigger change in my momentum. So this is going to create a bigger change in momentum because I have a bigger force acting over the same time,
amount of time.
which is going to take a steeper slope here because the slope of this represents force.
Oh, shit.
Gosh,
Dang it. It's the physics ghost.
I hate when this happens.
How come we didn't get to do cool projects like this, Bird?
Huh? You didn't want those problems, trust me. Those suck. Okay, now, if I take the 200 gram mass, and then I take the 1 kilogram mass off, okay, and do this now, what's going to happen?
Real fast.
Okay?
Dang.
So,
That
what
was
happened to the
less than a
acceleration,
inch on the
Vonda?
ground.
It went up
Why?
because it has a smaller mass but the same force.
Beautiful. Okay? So I have less stuff.
What?
He's not your leaning
I
post.
was standing in front of him. I came back and I gave him a hug and I was just kind of hanging out.
Michael's
I leave
cool,
Michael.
man. Michael holds the door
I love
every day.
Michael,
I need him.
like physically.
No.
Michael always holds
Like,
the door
for my
for
staff.
us, so I thought I'd just give him a little hug for it.
Okay, good, good.
Michael, appreciate you.
All right. Now,
Apple always wins.
so if I take this off and let go of it, right? What happened to the change in momentum? It's the exact same. Why?
Because there's less mass.
But it's the same force acting over the time. Okay? But why is this one going faster?
Because it has a smaller mass.
So to create the same momentum, it has to be going faster. Got the idea?
Yes.
Okay. Back.
No, camel torque is my favorite.
I mean,
Okay. So here I have a raw egg.
we all just eggs
I'm gonna
for
throw it to
real.
you.
Oh, yeah.
Okay?
Charmin ultrasound tan.
Now, here's how you can always tell if it's raw egg. If you spin it and you stop it and it continues to spin, it's a raw egg because the inside has angular momentum. Okay? If it was hard boiled
Yeah,
and you stop it, it
And
won't
the kitchen
continue to
suit.
spin.
I use that all
So
the
if you
time.
spin it, stop it.
I thought there was
Wait.
something like if it floats.
You could be lying to us.
Can we
I
have,
could be.
yeah, can we have Max verify it?
No, that's
No,
true.
no, we will
That's
later.
definitely
later. That's
So here's what I'm going to do.
Gotta wait for that.
I'm going to throw this raw egg to Brie, and the trick is I don't want it to break. Okay? This isn't, we're not trying to spike, doing the set thing. Okay, you ready? Ooh, nice. Now, what did you do when you caught it? Why? Why did you move your hands in the direction of the egg? Why didn't you just go boom?
Because it would have broke.
Why?
Because, I don't know.
What did you do by moving your
Well,
hands?
like straddling it
Down.
instead of like
Slows the
just.
momentum.
Oh, hold on, whoa. What did you do with the time? When to catch it, when you moved your hands, what happened to the time? Keep that in mind. Now, give me that egg back.
Yeah, I don't want it anymore.
Okay.
Put the brake in.
All right.
Oh.
Okay.
Yeah.
Why'd you put it upside down?
Huh?
Oh no, never mind.
Upside down.
I thought you put it upside down.
Good.
Hey, shut
So
up, Matt.
now, oddly enough, does this graph represent me throwing the egg and Bree catching the egg?
Yeah, sure.
Yep. I think it does, because I started with the egg at rest, right? Threw it, traveled through the air, Bree caught it.
Yeah.
Okay? Now, Bree took this idea and she cradled it. So, what's going to cause the egg to break? Acceleration or force?
Force.
Force, right? Okay? Force is going to make it break. Too much force, egg breaks, right? So here's what I want to look at. We said that this momentum is Newton seconds, and this is in seconds, and the slope of that line represents force, right? So by cradling the egg, if the more she cradles it, what happens to that line? It becomes
Shallow.
less steep. So if the line becomes less steep and the slope represents force, your force is becoming smaller. Okay? So this is a situation where probably even in second or third grade, if I threw you a raw egg, you all would instinctively cradle that egg. You have no concept of the impulse theory, okay? And this is technically what this is called. So whenever you change the momentum of an object, it's called an impulse, okay? So I imparted an impulse onto the egg. Bree imparted an impulse onto the egg, okay? Now, so the impulse is changing momentum. So we both imparted the same impulse on the egg. Because I took it from 0 to some amount of momentum, Bree took it from that same momentum back to 0. Now, what would happen to the change in momentum? Listen to me very carefully. What would happen to the change in momentum if Bree just went like that and caught it? No. What would happen to the value of the change in momentum?
It increase.
It would
Steve, go to zero. Be the same.
It would be
Be the exact same. Why would the change in momentum be the exact same?
going up.
Yeah, it's still going from some value down to 0.
Oh, okay, change.
Now, what would happen to the rate of change in the momentum? Ah! So, the rate of change in momentum is reflective of the slope of this line. right? So when she has a shallow line like this, it's because that momentum is changing very slowly. If she just goes like this and catches it, it's a very rapid change in momentum, and the egg is going to be more likely to break. Okay? Got that? Okay, now, Mad Max, kind of give it a spin. All right, so here we go. Landon, here, come back here.
Oh, yeah. Make me some scrambled eggs.
Okay, I need you guys to hold up this side.
Please miss.
I don't even know what you would do.
Wait, are you gonna
We all just eggs for real. Need a bag for that?
We are not eggs for real.
We are eggs for
We
real.
are not eggs for real. I don't even know what this means.
We are eggs for real. That's what it means. We're all just eggs for real.
So,
Eggs in the wake of a tiger.
Eggs.
okay? There you go. Because what I'm going to do is I'm going to throw the egg into it. Now, get away from the wall.
There's yolk on this
I think I
blanket.
see a yolk.
There's yolk on the
That's
blanket.
already broken. Okay. So now,
There's the yolk.
kind of lift that bottom edge up, because so that it doesn't. Okay, here we go. All right, just kind of lower the whole thing down just a little bit. Hop up, there we go. Okay, lower the bottom down a little bit. There we go. Okay, perfect. Okay, so I'm gonna take this, right? We're gonna give it a throw into the blanket, right?
Oh, that's weird.
Or just. You gotta build up to it, man. All right. So we got that one, right? Egg get ready. So did I impart an impulse onto the egg?
Yes.
Why?
Changed it.
Changed the momentum. What did the blanket do?
Imparted an impulse.
It also imparted an impulse, but that impulse made the egg
Slow down.
slow down. Which one had the greater impulse? They're the same. Okay? The impulses are the same. Now we'll throw it a little faster. Now don't let go of it, because if it goes south, it's because you guys dropped the blanket. Ready? Here we go. Okay?
you ran?
Gotta build up.
No, it's just, no.
MLB bounce?
Oh, no. So, who's got the best arm?
Shively.
Shively?
Guarantee it.
Now, if you miss, which happened last year,
I remember
Okay.
that. I heard about that.
okay, so a young lad, I was doing it over here on this wall, and had the blanket here, and the young lad that threw it missed, and it hit like right between the door and the floor. It was like an asteroid hit the earth. It scattered all the way to the lab tables in the other room. It was horrible. Okay,
So good.
so wherever you want to be,
Carson.
I feel better if you were probably a little closer.
Carson.
Okay?
If you miss, I'll give you $20.
You feel comfortable that I know you're not.
Carson, if you miss, I will give you $20.
Skip it off the desk.
Comfortable right here.
Okay, all right.
Take a little crop up like you did.
Oh yeah, you can go hop if you want, but don't miss.
Is your shoulder loose?
Just please do this for the entertainment.
Oh, man.
Yeah,
They deserve to see it.
This one's for you guys.
That was
That was a practice.
That's practice. Okay, so let's have full speed.
Make Jason
Full speed. Okay? Ooh. That was nice. Okay, so, they didn't break, right? Well done. Well done.
Bird, can you break the egg in your hand?
No. But
Max?
if I take that same egg, though, and drop it from just this height,
Garrett.
okay, fine. Okay.
You got really excited.
That was Vonda, for those of you who don't know.
Okay. So if I take this, ready? You ready, Vonda? I don't want you to listen. Okay. If I take that same egg and just drop it from this height, what's going to happen?
It's gonna break.
Oh. Okay.
Yeah.
Oh yeah, it broke.
Oh, not the chicken.
Oh,
There's a reason you're the closest one to that.
I could have gotten used out of that.
Wait, do you have another egg that I can prove Matt wrong with?
Little sound, no, never heard that.
Yeah, no.
Can I get some?
No.
I didn't even
So-
get any sound.
Here's the question. So Shively could throw it as fast as he could into the blanket, and it didn't break.
It's crazy.
But I dropped that egg from this far, and it shatters.
Yeah.
What's the difference?
There's give on the blanket.
The rate.
Really nice and soft.
The amount of force.
Amount of force
The biggest change in momentum.
The acceleration.
The rate of
How
change.
slow?
is the rate of change in the momentum, right? So imagine if Shively had thrown the blanket, or thrown the egg into the blanket, but he sailed it over the top. What would this graph do?
It would go just.
Okay?
Right into the wall.
Basically, it would go straight down. What guaranteed, what's the egg going to do?
Slow.
Egg's going to shatter, right? Because there's going to be such a rapid change in momentum. So it isn't the change in the momentum that causes damage. It's the rate at which the momentum changes. Now, anybody here ever do gymnastics? I'm sure you did. Shut up.
I did.
Seriously.
Yeah, I was
Yeah,
like
he did the
three.
rings.
Oh yeah, actually I did when I was like 2. I wasn't good at it, which
I'm
is why
guessing
they...
Tori's done more than any of us have, right?
Yeah.
So what was the first thing they taught you about landing in terms of what you do with your knees?
Bend your knees.
Why? Why? What does bending your knees do when you land?
Lessen the impact.
It's your menisci.
In terms of this equation, it's the
Increases
blanket.
the rate of
Biology.
change.
No.
Decreases the rate.
It decreases the rate of change by increasing the
Time.
That's
time.
what I meant.
Okay?
I should.
Wicked.
So when you land with your knees bent, right?
Yep.
Michael?
Okay, so,
What?
like bend your knees and then jump, so you can get like, jump higher.
More spring in your step.
We'll hold that thought till Monday,
Okay,
okay?
Biology.
We'll get into that Monday. You ask me that question on Monday,
okay.
okay?
Berg, I have a prime example of what happens if you don't bend your knees.
Tell me.
On my knee, you get like a 12-inch scar.
Oh,
Run on a skate park.
I jumped off something like the size of this table and I landed and I tore my patellar tendon.
Yeah.
Everyone
No.
bend your knees.
Yeah, wasn't your kneecap like way
Yeah,
up
my
there?
kneecap was like right up here.
oh.
Oh, yeah.
I jumped off something like this and I landed. Snapped
right there, so his
patellar tendon,
kneecap
my
was
kneecap
up
went in my
there.
thigh.
Yeah, like you landed
Right
on the
away,
corner
you
and it
knew
just
something
pushed
was
Oh,
it
I didn't feel it. And I went to stand up and I couldn't get up. And I looked down and my kneecap's right here.
What, how old were you?
8.
Oh my god, dude.
It was last week.
I don't imagine just seeing your
That's a
kneecap.
life-changing
How's that
experience.
anatomically like possible for your kneecap to just?
It's not
Your
attached.
patellar tendon
not
bolted.
Because it's inertia. So when you landed, there wasn't anything below the kneecap, it kept going up.
Biology is physics.
So no, here's the deal. Every time physics meets biology, who wins? Physics.
Whoever you like more.
Yeah. Physics always, like rock, paper, scissors, physics always beats
Is that because
biology.
biology says
Okay.
Fair use Jesus.
Now,
We got volcano in this.
what's the function of seat belts and airbags?
To keep you, to stop your inertia from moving you forward.
It increases the time to decrease the
Rate of change.
rate of change in momentum, which decreases the force. Okay? Cool with that? Simple. Got that? Simple, right? Simple. All right. So if you're an engineer, if you're an automotive safety engineer, you wake up every morning trying to increase the time to decrease that force. Okay? That's every morning. That's your job. Because fundamentally, that's what makes cars safe. Now, let's look at this. So we said, if we had a force time graph, right? The area under force time graph represents what? Change in momentum. Okay? So let's look at two situations. Now, as you get into this, you have to realize that change in momentum can equal like two different things, okay? It equals two different things. One option is that change in momentum equals mass times change in velocity, okay? That's one option. So this is why this is kilograms meters per second. This can also be written as mass times V minus V naught, okay? Works the same way. It could also be written as force times time. So let's look at two situations. Situation number one, here's this car, right? Starting from rest. V naught equals 0, and we're going to speed it up to like 10 meters per second, and it has a mass of 2 kilograms. Did the momentum change? Vonda, did the momentum change?
Yes,
Yes. Why?
because there was acceleration.
And the velocity went from 0 to
10.
10. So we changed the momentum, right? So, do we have enough information to calculate the change in the momentum?
Yes.
Yeah, I've got the mass and I've got the initial velocity and the final velocity. So my change in momentum would be 2 kilograms times my final velocity, which is 10, minus 0. So what's my change in my momentum? 20 Newton seconds, or 20 kilogram meters per second. I don't care. Okay, one of the two. Is that enough information to calculate the force?
Well, we need time.
How?
Don't we need
Because we
time?
multiply it by time.
No,
We don't have time.
Just kidding.
so no.
So no. Can you calculate the change in the momentum? Yes. But you can't calculate the force because you don't know time. Now, if I told you that that time was 4 seconds, now could you calculate the force?
Yes.
Why?
Because you can multiply it.
We got time. We got.
Well, remember, force times time equals change in momentum. True? Do we know the change in momentum at this point?
Yes.
So if I take my change in momentum, which is 20 Newton seconds, and divide that by the time of
4 seconds.
4 seconds, I get a force of
5
5 newtons. Okay? Now, here's what that means. If you were to look at this in terms of a force time graph, okay? Force time graph. What would the force time graph look like?
A horizontal line.
At where?
5.
Horizontal line at 5 newtons, right?
Yep.
That's going to act for
4 seconds.
4 seconds. And if you were to find that area, that would equal 20 Newton seconds, which is my change in my momentum. Okay? Now, so this is you driving, okay? So let's say Grandma borrows the car and Grandma's going to drive, okay?
Speed reduction.
Grandma does it in 1 second. Grandma has nothing to live. It's like, I've had a good life.
That is literally my grandma. He literally drives insane.
Okay? I didn't say Grandma was a good driver. I'm just saying she's going to do this in 1 second. Now, listen to me very carefully. Grandma makes this change in 1 second. What happens to the change in the momentum?
Stays the same.
The change in the momentum is the exact same. Why? It's still the same mass, it's still the same change in the velocity. So the change in the momentum is the same. This is where you have to focus on what you're holding constant and what you're changing. Okay? So in this situation, this is staying the same. Cool with this? Cool with this? Now, but what's going to happen to the force?
Increase.
It's going to increase because we're going to have the same change in momentum in
1 second.
1 second. So then I'm going to take 20 Newton seconds and divide it by 1 second. I'm going to get 20 newtons. So how's that going to change this graph?
It's going to be a longer.
You're going to have 20 in your
No.
Yeah, it's going to get steeper I mean, it's going to be taller, but it's not going to be as wide. So here's the deal. I can either have a small force acting over a longer period of time, or I can have a larger force acting over a shorter period of time. Are these two areas going to be the same? Yes. Now, here's what's important. I'm keeping, in this situation, the change in the momentum the same. Okay? The change in momentum is the same. That's the same mass and the same change in the velocity. Now, what if I wanted to create a big change in momentum? What would I want to have in terms of force, and what would I want to have in terms of time? Would I want them both to be big, both to be small, one to be big, one to be small?
One big, one small.
Which one?
Force big times small.
Okay? Why?
Because that's going to give you, well, I guess you could also have, you're just talking about change, not about the rate.
I want a big change in momentum.
You could also have a long time, low force, it's going to give you the same area. Force.
Mad Max?
I'm gonna say you're wrong because
Why?
you want a large force over a large time because
Why?
then the force has more time to change the momentum more.
Yeah. Because if I have a large force over a long period of time, guess what? That's going to give me my biggest area, which is going to give me my biggest change in the momentum. Okay? So, Mad Max, solve that.
14 whole questions.
You're dang right it can.
Now,
I need to use my toes to
here's
count
the
that.
deal.
I don't have toes. Whose hair is this? Mine.
Now, when you get to question number 8, okay, I'm going to say sketch a force time graph, okay? Literally, this is a sketch. It doesn't have to be done on graph paper. If you want to do it on graph paper, you can. But primary thing, if you do it on your piece of paper, just draw it big enough where everything is clearly labeled, because you're going to use that graph on number 8, and then when you get down to number 10, you're going to go back to that graph and you're going to have to add on to it. Okay? So you're going to have to do 2 different things with that graph. But other than that, you're on your own. So
Off to the races.
Yeah.
go off to the races.
This is